All right, today we're diving into one of the most critical pieces of equipment in any large building, the transformer. It really is the unsung hero of your electrical system, and trust me, getting the selection right is absolutely everything.
Because that's not an exaggeration. That's exactly what's at stake. A single decision, made right at the design stage, can impact everything from fire safety to your operational costs for decades. So let's break down what that choice really involves.
So what does a transformer actually do? Well, think of it like a translator for electricity. It takes this huge, powerful, high voltage from the grid and steps it down into a safe, usable voltage that can power a building. We're talking about the juice for everything, from the lights above your head to the life support machines in a hospital.
And that brings us to the first big fork in the road for any electrical engineer. This is the fundamental decision, and honestly, it dictates almost every single thing that follows in the design and installation.
So, what are the trade-offs? Well, on one hand, you've got your traditional oil-filled transformer. Its biggest selling point? It's cheaper up front. But, and this is a huge but, it's filled with flammable oil and needs regular maintenance. On the other hand, we have the cast resin, or dry type. Now, it'll cost you about 30 to 40% more to buy, but it's self-extinguishing, meaning a very low fire risk. And it's pretty much maintenance-free. So, let's imagine you're designing that hospital we mentioned. Suddenly, that low fire risk isn't just a nice feature, is it? It becomes a non-negotiable safety requirement. The cast resin unit is the clear winner, despite that higher price tag.
And these differences have this cool ripple effect through the whole system design. Fire safety basically tells you where you can even put the thing. Maintenance hits your long-term budget, and then there's this thing called impedance. Cast resin units tend to have a higher impedance, which can actually be a secret weapon. A higher impedance limits the potential current in a short circuit, which could mean you can use lower rated and therefore less expensive switchgear downstream. It's this fantastic balancing act of cost, safety, and overall performance.
Now let's see how transformer placement can literally make or break your building's electrical design.
In a perfect world, you just stick it on the ground floor, right against an outside wall. Super easy access, great natural ventilation, job done. But in a dense city, that space is a luxury. So basements are really common, but then you've got to worry about flooding. And a high-rise tower? Now you're talking about putting a 4-ton machine, that's the weight of 2 large cars, on an upper floor. That's a massive structural challenge. And your choice of oil-filled versus dry type is often what makes one of these locations possible and another one a total non-starter.
And here's exactly why we're so obsessed with location and ventilation. A single 1600 kVA transformer running at full blast is kicking out over 20 kilowatts of waste heat. To put that in perspective, that's like running more than a dozen high-powered space heaters in a tiny room 24/7. If you don't get that heat out, you are literally cooking the transformer and drastically shortening its life.
Okay, so let's say your hand is forced. You have to install an oil-filled unit indoors. How on earth do you manage the risk of having a giant tank of flammable, environmentally hazardous oil inside a building?
You have to build a catch pit. This is basically a concrete basin designed to hold every single drop of oil in a worst-case leak. But here's the kicker. It's not just an empty pit. It has to be filled with a special type of gravel, which means the total volume of the pit has to be about 3.6 times the volume of the oil itself. This is a perfect example of how that cheaper transformer suddenly comes with some pretty significant hidden construction costs.
But heat isn't the only invisible force you have to wrestle with. Transformers also create noise and vibrations, and if you don't manage them properly, they can become a major headache for the people in the building.
You know that classic humming sound? That comes from something called magnetostriction. It's just the transformer's metal core vibrating very, very fast. That vibration can travel right through the building's steel and concrete, creating a mysterious humming noise floors away. That's why it's absolutely critical to install them on anti-vibration mounts and use flexible connections to isolate them and trap that noise at the source.
Now there's a common trick to get more power out of a cast resin unit. It's called forced cooling, which is just a fancy term for adding fans. It works too. You can get a power boost of up to 40%. But there's no free lunch in engineering. Those fans add a lot of extra noise, and they actually make the transformer less efficient, nearly doubling the energy losses when it's under load.
Okay, we've talked a lot about the physical side. Let's get into the nitty-gritty numbers, the technical specs that form the real backbone of the whole electrical system.
We mentioned impedance earlier, and this number is so important. It basically tells you how much current could flow in a worst-case short circuit. So for example, a standard transformer might be able to unleash a massive 58,000 amps. To handle that, you need incredibly expensive, heavy-duty switchgear. But, and here's a great little engineering tip, by specifying a slightly higher impedance, say 6%, you can knock that fault current down to a much more manageable 48,000 amps, and that might be just enough to let you use standard, more affordable equipment.
Next up is something that looks really complex on paper, the vector group, usually written as DN11. It sounds intimidating, I know, but it's really just a shorthand. It's a code that tells engineers two crucial things: how the wires inside are connected and whether multiple transformers can work together as a team.
And this diagram breaks it down beautifully. The D is for a delta connection, which looks like a triangle on the high voltage side. The Y is for a star connection on the low voltage side, which gives us that all-important neutral point N that every building needs. And the 11? That just describes the timing difference between them, just like the hands on a clock at 11. It's a simple, elegant code that makes sure everything works together perfectly.
Okay, so we've looked at all these different pieces of the puzzle. Let's pull it all together now and see why these initial design decisions have such a massive and long-lasting impact.
Modern transformers are incredibly efficient. We're talking over 98%. But they're not perfect. They have two kinds of energy losses. No-load losses are there constantly, just from being switched on. Load losses happen when the building is actually using power. These numbers look small, but remember, this machine is on 24/7 for decades. All those little losses add up to a huge lifetime energy cost, not to mention all that extra heat the building's cooling system has to remove.
So here's the bottom line. The choices made in the design phase echo through the entire life of the building. A decision on day one affects the ease of installation, the efficiency of operation for the next 30 years, and, this is the one people always forget, the cost and difficulty of replacing it. If you don't plan an access route to get that old 4-ton unit out, that final step can become an absolute logistical and financial nightmare.
And really, it all comes down to this. Choosing the right transformer isn't just about voltage. It's about safety, efficiency, and longevity. It's a masterclass in thinking about the big picture, balancing upfront costs with long-term performance and reliability.
It kind of makes you wonder, right? So what invisible engineering choices are keeping your world running right now? What other hidden workhorses like this are humming away in the background, making everything possible? It's something to think about the next time you flip a switch. Thanks for watching.